Section 4.3 is called Greatest Common Divisor and Least Common Multiple. The first thing I'd like to make a comment of is about English. You didn't know you're in English class, right? The comment I'd like to make is about the words greatest and least in this statement. The word greatest, do you know what part of speech that is? Oh, I don't know about that. I was thinking adjective. Adjective is the one that I want it to be right now anyway. It is an adjective because it's describing something, right? That's what an adjective, it may be that too, I just don't know, Emily, because see, I'm not an English teacher. So, adjective, for sure. It's an adjective describing what? The common divisor, and in particular divisor, because common's actually another adjective. So it's actually an adjective describing divisor. So the word greatest refers to the greatest of the divisors. And the word least refers to the least of the multiples. So please be very careful to understand that a greatest common divisor is actually smaller than the value you're working with. It could be the same size as, but typically we're talking about something smaller. Okay, so greatest does not mean big here. It means it's the biggest of small things. Right? You know how that works, right? I'm the tallest female in my family, but that does not make me tall. That's how I am. Okay. Least common multiple does not mean the number small, and in particular, it's larger. It's as least as large as, but it's usually larger than the number you're talking about. Okay? So be really careful about the language here. Don't think that those words mean small or big. They're all in relation to what they're referring back to in their nouns. Okay, so we're going to talk first about greatest common divisor. A greatest common divisor, also sometimes called a greatest common factor, abbreviates acronym to GCD or GCF. You've probably seen this before, is the greatest whole number that divides all numbers in your set. So this will always exist because it always could be what? What's a number that's going to divide 1? There will always be one of these. It may be a very small number, 1, but there's always going to be one. Okay? Now, we encountered this word a couple class periods ago. I used it. We didn't define it, but it came about in our discussion of examining the rule for 6. Do you remember that? The reason we know a number is divisible by 6 is if it's divisible by 2 and 3. Well, relatively prime is that word that came about. Relatively prime means that 2 or more numbers that have a GCD that are actually equal to 1. In other words, they have no common factors other than 1. So when numbers are relatively prime, it doesn't mean that they're actually prime. They could be, or maybe one of them is and one of them is not. But what it really means is that they don't have anything in common among all of them. And you notice it also says 2 or more, right? So we could be talking about 3 numbers or 4 numbers that are relatively prime. Most of the time we're going to be looking at 2. All right, there are several methods for finding a greatest common divisor. The first one we're going to look at is called the intersection of sets method. So this method lists all the divisors of each value out. Okay, so this is not prime or composite issue here, right? This is all divisors. So we're listing all the ones that are prime and all the ones that are not. And then finding the largest divisor that the 2 lists or 3 lists, whatever, have in common. This works pretty well if the numbers are kind of small. If the numbers get too very large, this ends up being a little bit cumbersome. We should do one with small numbers, of course, 12 and 15. Okay? So we're going to try the number 12, and what we're going to do is we're going to list out all the factors of 12, and as we start, we're always going to start with 1. What is the next divisor of 12? 2. And if you want to, you can go in pairs, right? We know it's 1 and 12. 2 and 6. What comes after the 2? 3 and 4. And there's no more space between the 3 and the 4, right, in terms of whole numbers. So we're done. So this is the list of all divisors, composite and primes of 12. We'll do the same thing for 15. 15, we can always write down 1 and 15. What's the next divisor, small divisor of 12, or 15? Yes, 3. 3 and 5. And there is one number between 3 and 5. It would be 4, right? And does 4 divide 15? No. And all we're doing then is we're looking at this list and we're looking for the biggest thing in both lists that they have in common. and the correct value here would be 3. So we would say that the GCD, and I'm going to show you notation, the GCD of 12, 15, okay, so the greatest common divisor of 12 and 15 is 3. Now, this is great if the numbers are small. Agreed? And a lot of books start with this method. They start with looking at divisors of things because they're starting with small numbers to begin with. So this is a very common method. Another method, prime factorization. This is also a very common method. Instead of worrying about what numbers are prime and composite both, you only look at the primes. And instead you take the number and you break it down into its prime factorization. So you break down 2 or 3 or 4, however many numbers you're comparing, into their prime factors. And then you choose or look for all of the factors that are in both or all 3 factorizations. So they all have a 2 in them, then we use the 2. If 2 of them have a 2 in them and the third one doesn't, we don't use it. Okay? And then we list each prime that is common to both or all values with the smallest exponent in any of the factorizations. And I'll explain that in a minute. And then on number 4, we actually find the product. That is, we multiply the value back out. All right, so I know you've used this method before. The numbers you can see, obviously, that we're picking here are a little larger than the last one, right? It's not 12 and 15. So we're going to take the numbers one at a time and we're going to find their factorizations. And because you're not as comfortable and familiar with it, I'm going to do the division algorithm like I showed you before. So what is the smallest prime number that divides 400? 2. And that gives me a 200, which divides by 2, which gives me 100, which divides by 2, which gives me 50, which divides by 2 and gives me 25, which divides by 5 and gives me 5. So there are only 2's and 5's here. And this is 2's, or how many 2's are there? 4. So this is 2 to the 4th. And how many 5's are there? 2. So it's 5 squared. So this would be the prime factorization of the value 400. We're going to do the same thing with 360. Smallest prime number that divides 360 is 2, and that gives me 180, which divides by 2, giving me 90, which divides by 2, still giving me 45, which divides by, it does divide by 5, but there's a smaller prime that it divides by. 3 actually works. Do you know what 45 divided by 3 is? It's 15. 15 divides by 3 again, giving me 5. So on this one I have a 2, I have a 3, and I have a 5. How many 2's do I have? 3. How many 3's do I have? And how many 5's do I have? 1. Okay, so like all of that's really like review from section 4.2 that you guys have just been working in. Okay? Or you're about to be working in with your group work. All right, but the part that's new from this section is to take a look and to see what do they have in common. So what prime numbers do they have in common? 2 and 5. And so basically we're at the point where we're at step 2. Step 3 says to list them with the smallest exponent. So what's the smallest exponent on the 2's? A 3. And the smallest exponent on the 5's? A 1. Now the reason that we use the smallest exponent is because what we're really looking at is how many of these things they have in common. Like if we went back up to the factor division steps themselves, we would say, look, 2's in common. Look, this 2's in common. Look, this 2's in common, and there are no more 2's in common. They both have 3 2's in common. They don't have any 3's in common, but they both also have a, 5 in common. That's what we're really looking at. And so when we look at the smallest exponent, we can see that. So the smallest exponent is what they have in common. What is 2 cubed? It's 8. And what is 8 times 5? 40. So 40 is the greatest common divisor of 400 and 360. Is it okay? All right, so this is the prime factorization method. The next method is called division by primes. Now, unfortunately, that sounds a lot like prime factorization method because they both have the word prime in them. So be very careful if you get to the test and I specifically ask you on one of them to use one of those methods that you're using the right method. Same for your homework, of course. Sometimes you get to choose the method you use and sometimes you are told which method to use. So this method is different. What we do is we write the numbers in a row that we're comparing, and we divide each of the numbers by a common prime factor. And we do that process again, dividing those quotients by a common prime factor until they have no other common factor between them or among them. And then the GCD is the product of the primes. So let me show you what this looks like. This is my favorite way. This method here, this is the one that I have been most familiar with most of my life. But this next one is one that I have been introduced to since I've gotten older, and I really like it. I think it works really well. All right, we've got the numbers 410 and 360. And we write them, like it said, in a row. In other words, beside each other, but with a little space, so we don't think that it's one number. And we're going to do division, much like we did on the previous slide, but we're going to do it with both numbers at the same time. What is the smallest prime number that divides these two? 2. And I'm going to divide them both. So this is now 205 and 180. Now, will they both divide by 2 again? No. How about 3? No. How about 5? Yes. So now, what is 205 divided by 5? Should be 41, right? And what is 180 divided by 5? 36. I don't need to go back and ask myself about 2's and 3's, because I already did that. Will both these numbers now divide by 5? 7. 11. And I've gotten way too big already, right? Because the numbers are only 41 and 36. I'm done. The answer is the product of the things that I divided by. So the answer here for the GCD is 2 times 5, or 10. I feel like it has a lot of the same benefits as the last method. I just don't actually have to write down the whole factorization for it because it really doesn't matter that 36 is a composite at this point. It doesn't make any difference because it doesn't have anything in common now with 41. And that's actually the question asked me about, was whether it had anything else in common with the other value. So I get to stop without doing as much work. Last, greatest common divisor method. This one is the most unique from the others. It's called the Euclidean Algorithm. And the process is not terribly difficult, but it does look different. So what you do is you divide the larger number by the smaller number. You divide the previous divisor by the remainder, and you keep repeating that process, and then the last divisor is the greatest common divisor. And unless I show you an example, probably that just went right over your head, because it would have me. This doesn't look like it makes a lot of sense. But the process is actually not too bad. Okay, you guys ready to try one? Okay, 72 and 126. The first step's easy enough. It says divide the larger value by the smaller one. So here's 126, we divide by 76. And your calculator is your best friend on this because I really don't want to test whether or not you can divide. That's not my point. Oh, I'm sorry. Thank you very much. Get the right values or you're going to get the wrong answer. How many times does 72 go into 126? Once. What is 1 times 72? 72. And if I subtract, what do I get? 54. Okay? The second step is to take the divisor and the remainder and do the same thing. Now that remainder better be smaller than the divisor or you made a mistake already, right? So we're going to divide what was previously on the outside, 72, by the remainder, which is 54. So how many times will 54 go into 72? Once. 1 times 54 is obviously 54, and if I subtract, what do I get? 18. I take the divisor and the remainder, and I do it again. 18, the remainder's on the outside, the divisor, 54, is underneath. How many times will 54 go into 18? 3. What's 3 times 18?
54.
54, and I get a 0 remainder. This tells me that I stop, And that tells me also that this is my answer. The greatest common divisor is 18.
Will you always end with a 0?
It will eventually hit 0, yes. It might not hit 0 until you divide by 1, though, Ashley. And then the greatest common divisor could be 1. But it will always eventually give you 0 as a remainder at the end if you keep doing the process. And once you get the 0 at the end, it's the last number you divided by. Okay, any questions on those?
What were you just saying about the 1?
Ashley asked me if this will always happen. That is to say, if you will always get a 0 here at the end. And the answer is yes. You may have to go through more than 3 times of dividing. That's possible. And it may be that the last division you do is by the number 1, which ends up being sort of strange, right? But eventually you will get to a point where you will get a remainder of 0. And once you get that remainder of 0, whatever number you divided by last will be the answer to the question, what's the greatest common divisor?
So it might be a 1.
It might be a 1, absolutely. And plenty of numbers have their greatest common divisor as 1. And let's see if you guys remember from the very first slide. Don't look at your paper, look at me. What do we call 2 numbers whose greatest common divisor is 1?
Relatively prime.
Relatively prime, very good. Okay, and I think that's it for GCDs, right? Yep. Okay, so we're going to stop there.